In this module, we will explore energy and rotation. Consider a collection of particles, each moving with some speed. The total kinetic energy of this collection of particles is given by the usual formula, but summed up over each particle in the collection. But if this collection of particles constitutes a rigid object rotating with angular velocity omega, so that the speed of each particle is related to its distance from an axis of rotation by the usual formula, then we find that we can express the kinetic energy as 1/2 times the moment of inertia of the object times the angular velocity squared. So we find that an object with moment of inertia I about its axis of rotation, undergoing rigid rotation with angular velocity omega, has what we call rotational kinetic energy. From the work kinetic energy theorem, we know that if a rotating object changes its rotational kinetic energy, then work must have been done on the object by a force. We can express this rotational work in terms of torques acting on the object. The infinitesimal work done by a force acting over an infinitesimal displacement is given by the formula that d work is equal to F dot d displacement. For rotation, we know that this infinitesimal displacement is equal to r times d theta. In vector form, this is written as ds vector is equal to d theta cross dr. So, using a little bit of vector manipulation, we find that the amount of infinitesimal work is equal to the torque dotted in with d theta. Now, it's important to remember that d theta is like the angular velocity. Its direction is parallel to the axis of rotation and is determined by the right-hand rule. That is, we wrap the fingers of your right hand in the direction in which theta is changing around the axis of rotation. Your thumb then points in the direction of d theta. If the axis of rotation is fixed and the torque is constant, then we have the total work is equal to plus or minus the magnitude of the torque times the total angular displacement. The plus or minus sign comes from the fact that for a fixed rotation axis, the angle between the torque and d theta is either 0 degrees or 180 degrees. You must be sure to check the directions of these vectors each time you compute the work done by a torque. The rate at which work is done on a rotating object is given by the power being equal to the torque dotted in with the angular velocity. This is in direct analogy with the translational version, which says that power is force dotted in with translational velocity. Again, if the axis of rotation is fixed, then the power is just plus or minus the magnitude of the torque times the magnitude of the angular velocity. However, for fixed axis or not, there is no need for the torque or the angular velocity to be constant. The power is an instantaneous quantity, and only the values of the torque and the angular velocity at that instant matter. Scenarios we encounter sometimes include a sphere or a cylinder rolling without slipping along some surface. Rolling without slipping means that the relative speed between the rolling object and the surface at the point of contact between the rolling object and the surface vanishes. So if the object is translating with a center of mass speed of v sub cm, then we find that the relative speed of the top of the rolling object is twice the velocity of the center of mass. These values come from the fact that the tangential speed of the rotating object is going to be equal to the center of mass velocity of the object relative to the surface. Similarly, we find that for any rolling object which is rolling without slipping, the speed of the center of mass is going to be given by the radius of the object times its angular velocity, and the translational acceleration of the center of mass is going to be given by the radius of the object times the angular acceleration of the rolling object. The kinetic energy of the whole rolling object can be given as a sum of the translational kinetic energy and the rotational kinetic energy. Because of the relationship between the velocity of the center of mass and the angular velocity, we can write this total kinetic energy either in terms of the center of mass velocity or in terms of the angular velocity of the object. Interestingly, we can treat the same scenario as if the rotation was occurring instantaneously about the point of contact with the surface. That is, we still find that if we consider our axis of rotation to be that point of contact, the speed at the axis of rotation is going to be 0 because the radius is 0. The tangential speed at the center of mass is going to be r times omega. And because the point at the upper side of the rolling object is twice as far away, its tangential speed is 2r times the angular velocity. So if we then look at the moment of inertia about the point of contact, we can obtain this from the parallel axis theorem. And because the distance in which the axis has translated is the radius r, we find that the moment of inertia is just ICM plus mr squared. If we now calculate the rotational kinetic energy about the point of contact, we find that the result is simply exactly what we calculated before as the sum of the translational kinetic energy plus the rotational kinetic energy about the center of mass. Until you become more experienced with rotating systems, it's probably best to always calculate the total kinetic energy of the object as the sum of the translational kinetic energy of the center of mass plus the rotational kinetic energy around the center of mass. Otherwise, you might accidentally add in the translational kinetic energy twice.